Hey now, I'm back. Mr. Angus Wangus making a video. Feels like I've never made a video before. Arnold, I'm back. Here, maybe this is more appropriate. I got another one. Ah. Anyways, I'm back. It's been a while since I made a video. I've been working on an idea and reading and studying and testing things that I want to test and see for myself, and working real hard to salvage things to be able to test with like I want to test them, and frankly been trying to make a electric motor that runs itself. And this video is going to show you the concept behind that. I'm not making a video to make claims of our unity. I think that's pointless on YouTube at this point now, in my YouTubian delvings. But no claims of over unity, although I could show you things if you were here at my place. But anyways, I want to show you the concept, and you can do it for yourself. It's awesome. I'm not going to put my name on anything here in this video. No Wangus motor, Wangus gen, or anything like that. I'm just sharing what I've learned in this time that you haven't seen me. So others can try things for themselves, you know, and experiment with it and make an over unity machine for themselves. If you choose to listen, right? Hopefully you do. My hope is that those with resources, I've learned, it's a horrible thing to say, but I've learned a lot about this topic. I've written a little research paper on the topic too, which you're not going to see yet. Maybe that's kind of like an artist who makes art. I'm not an artist, right? So I imagine they have a hard time maybe sharing it with everyone when they're done. But anyways, that actually it's done. I just have to polish it up, and you know, it's embarrassing to me, kind of, because it's not what I went to school to learn for, or to learn, you know. It's not what I'm trained in, writing research papers, but, you know, it's good. I'll never be happy with it, sort of thing. But anyways, I'm back, and I want to share that concept with you, and my hope is that people with resources will be able to apply what I'm, you know, will listen and apply what I'm showing here in this video, and also share what they do. But because I don't have the resources, that's what the point I'm at right now. I have to get more wire, frankly. Maybe more core material, that would be cool too, but I know exactly what I'm doing and the path I'm going, and you'll see that, and you'll be on the same path, right? This is what this video is all about. I wanna show you what I've learned and share it, right? It's taken me a long time learning all that I have. I've been building a machine, but it's always morphing, right? So I have things to show you here, demos and things, but that's where I'm at. I'm gonna start sharing things. I'm gonna be making videos, you know, but the underlying concept is what I want you to learn here, and you know, a lot of it is stuff we already know. There's no magic, you know. It's very cool. I can relate it to Ed, and have in the past actually, and it's very close to being on the money. But the underlying topic is kind of the 800-pound Sasquatch in the room, right? That we all nonchalantly act like is normal. But, you know, we need to dissect it. We still haven't dissected it. Really, we haven't. But I can relate it to Ed, and that's what he was doing. Ed's a master, and I'm going to show you what he was a master at. And we can all, this video, the things I'm going to talk about in it, nothing's new. There's nothing new under the sun, as Ecclesiastes tells us. I think that's where it's come from. But there's nothing new under the sun, right? It's just things that have been sort of suppressed. I'm not going to get on an oil company rant, but you know, they discourage, they steer science and society, and believe it or not, they do. They steer it, and they use their money to do it, and this is something they've always steered people away from. I see it now, and want everyone to see it. People with resources that can make it happen faster than me. I'm not about greed or money or pride or any of that. Anyone who knows me knows that. But anyways, Ed knew a lot, and he knew funky things, but it's not magic. He wasn't a magician, as some people out there would like to have you believe. He just wasn't. Period. So we'll be talking about all that. But what I have for you is, first we need to talk about resonance, reactance, our inductors, how this relates to the underlying concept. A lot of you have heard these terms before. I'm going to relate them all together. We've heard of reactance before, maybe. That's the 800-pound Sasquatch in the room right there. Reactance. And we're going to have a different look at it, right? A lot of us have heard of reactive power and seen people doing reactive power calculations. There was a video uploaded a few months ago of a guy sitting with a notepad in his lap and a calculator at a Tesla Tech conference with a group of people around him. And he was showing basically the exact same thing I'm going to show you, except that he, in all respect, I'm going to say this with all respect to him because he's a very smart dude, but he just needs to go one more level, right? And that's what this video here from mine is going to show everyone. He's sitting there with a transformer, met glass and all that, but he could make simple changes and do much, much better and have an over unity device. But that's what my video here is going to be talking about. Resonance, reactance, inductors, and how to tame it, basically. So after the little intro into that, then we'll talk way more in depth about reactant, the relationships between all these things. Reactance, inductance, frequency, resistance, impedance, Ohm's law. These things, none of them are independent. They're sort of all one being. They are. And if one moves, the other moves, and that sort of thing. And we're going to have a really, I could make a 24-hour video in depth, right? But we're going to have a little more in-depth look at that. And then after that, I have demos to show what I'm talking about. And I have the demos set up in Bedini style. This is my first clip I'm videoing, so I don't know how long this video is going to be. It's going to be a good length, so get your popcorn. But anyway, I want to show it in a motor style, and I thought Bedini, is something a lot of us know about, so I thought that would be appropriate. Bedini style, talking about tuning the copper and the iron. And this is what we don't do, is tune the copper and the iron. We tune the circuit, and we tune this and that, but we don't tune the copper and iron like the old timers did. So we'll have demos of that. It's going to be cool. It's not my project, and it's not as low as I can go on the old limbo pole. But you're going to see it's going to demonstrate what I'm talking about nicely, I think. You know, we'll see. So then after that, we're going to have a look at how this all relates to Ed Leedskalnin, his wheel he had there at Coral Castle, his PMH, you know, how all these things, reactance, inductance, frequency, resistance, impedance, and Ohm's law, and what Ed was doing with his setup. And after having a look at a little Bedini setup that I'm going to make in this with this nature in mind, you'll see, you know, how it relates to Ed's setup. So after we talk about Ed and Coral Castle and how it relates, then we'll talk about other applications, past applications, solid state, a solid state generator in this application, in my opinion. I haven't tried it yet. Maybe I could throw one together in a day. I don't even know. That's why I'm sharing this with everyone, because together we can get a lot more accomplished, which is always my intent. You know, I see people jumping around saying open source, right? But you think about it, you know, jumping around saying open source, who's that benefiting, right? What about the guy on YouTube that uploaded one video that's 30 seconds long, right? Is he not open source? You know, so. Anywho, I could go on a big tangent about that, but I'll spare you. We'll talk about past applications, other applications. The solid state, the solid state, in my opinion, would be much easier, and we'll see that, I think, when we look at these individual components, particularly frequency. That's where that would come in, but it would be easier, in my opinion. I haven't tried it. But also I want to talk about past applications. We hear fairy tales and stories of men from the past, Tesla and others, you know, all these others, Daniel McFarlane Cook, Stan Meyer, you know, he's dead, Hendershot. We hear these stories, fanciful stories, you know, about machines that ran themselves. Well, you know, you go back and read these patents again after listening to what I have to say here, and you'll see, you know, this is what they were doing, you know. So hopefully I'll be able to relate what I'm talking about to some past applications of it that people had, that I don't think they were maybe encouraged to explicitly explain to everyone in the world, right? Going back to oil companies and remembering how I could rant for days about that. But finally, then, I'm going to talk a little bit about where is my project headed, and where I'm going. You know, I need wire, and I'm going to talk about that briefly, but this is it. You know, these are the things I want to show you here in this video. This is the meat of the sandwich that I have been working on for months now, and the reason for that is, you know, basically so I could focus, right? I've shared as I learn on YouTube before, and it maybe people don't realize, but that really makes things difficult, and I was really trying to stay focused on the path of thinking that I was on. So that's the main reason for that, but I've always shared my ideas, and we'll continue, and I'm gonna have videos to come. So that was just a brief intro to our beginning here, and we'll get started here with the with the first look at resonance and reactance, and get started. Okay, so now I just want to briefly touch on the general thought of resonance and reactance, and start out by talking about resonance and how we think of it and what it is, sort of generally, and keep heading down the road of what I want to show. This is where we'll start. So resonance, what is it? It's thought of in a lot of different ways, described in a lot of different ways. It has to do with a lot of different things: sound, vibration, and a lot of different ways it's been described. The pushing of a swing, and the positive and negative energy, and using it to your advantage. But in an electrical sense, an electrical system, resonance truly is a balance between the capacitance and inductance. And as we tune a circuit, the happy median balance between the two, results in our best output for a system, an electrical system. Generally, in a generator sense, if we're talking about generators, an increase in voltage, we get an increase in voltage output, potential, with tuning our circuit, right? However we choose to tune it, adding capacitance, adding inductance, resistance to a circuit, changes these results and the output we get. But it's sort of a balance, and we tune our circuits, and in a sense of a generator, it increases our potential output. In a motor sense, it's going to decrease our current used, right? The input with tuning. And we see that with the Bedini. We tune our circuits with a variable resistor in series with the trigger coil, trigger winding, and it tunes the system down. And usually what happens is, depending on your inductor, and we're going to find all that out in the next clip. By the way, this isn't going to be just all clips of computer clips like this. The next clip I video is going to be the good old chalkboard, and you might see the back of my hand. Then the clip after that's going to be demos, so bear with me. I'm trying to make this watchable for everyone. A lot of this is going to be, things people have seen before. I really am making this video for guys who are seasoned a little bit with this type of information, because this is what we need to apply to our systems, what I'm going to be talking about in this video. But at the same time, I want to make this watchable for everyone and understandable for everyone out there. Nevertheless, just like with tuning with the motor, and just like with a Bedini, right? We tune our circuit, we add resistance, the current goes down, the consumption input goes down, and we find that what we call a sweet spot, right? And the wheel actually, in a lot of times, does more work. It goes faster, right? Which is very interesting. Hard to find specific explanations why that occurs, right? We call it resonance, we call it this, we call it that, but actual specific explanations for why that occurs, and by specific I mean mathematical, that's harder to find, so this is what this video is about too. We're going to show that with the Bedini. And what we find is, again, with our Bedini, we tune it and we add resistance there on our base, and we turn the resistance up, and the input current goes down. Now, it should lead us to a question, you know, and the question would be, can we alter the sweet spot? You know, like what if I don't want the sweet spot where it is on my Bedini, let's say. Now these thoughts don't just apply to Bedini thoughts. You know, all motors, all generators, right? Keep that in mind. I'm going to demo a Bedini and I'm going to mention Bedini, but this all applies to all motors and all generators. So let's say I have my Bedini motor and I have a sweet spot. I've learned how to tune it and find the sweet spot, right? And the sweet spot is the point of adding resistance where the motor accelerates, our input goes down, but we can go past that too with the resistance, right? And then it starts going the other way and the motor goes slower and the input goes up, right? So there's a sweet spot, we call it. But what if I don't like the sweet spot in my Bedini that I have made, right? How can I change it? What if I don't like where it is? You know, what if I want it to go, you know, faster? Or what if I want it to do the same amount of work and draw half the current? You know, what if the sweet spot was lower where I add more resistance? You know, how do we do that, right? Well, in the past, I've noticed, and probably others have noticed as well, if you have two different Bedini coils, bifilar wound coils is how he makes them. If you have one coil that has, let's say, similar dimensions but more wire on it, you might notice that the sweet spot changes and your coil is going to become more efficient with added resistance on the base. Your wheel probably go faster, right? You know, maybe you've noticed that. I have. So then the next question, you know, should be is, so what's happening, right? Why is that? What exactly is that? And again, we refer to it as resonance different terms like that, right? But what exactly, okay, resonance or imbalance, you know, we tune the resistor with that inductor and we get better performance, but why can't I get even better performance, you know, if I add more resistance, you know? Why, you know, what's happening? You know, we say resonance or we say different terms, but explicitly explained, you know, what's going on, right? So with that example in mind, you know, more wire on the coil, right, results in being able to add more resistance. And obviously the coil is going to have a higher inductance because it's larger, right? You have more turns, you have more resistance, measured resistance in the wire, right? Well, just from that, a coil having more wire on it, so more inductance and more measured resistance, those two things are key. You know, they're the two things involved in impedance and reactance, right? Inductance definitely is, you know, the way I think of it, half of reactance, right? So then you got to ask ourselves, why is that important, right? Well, it's important because we need to learn how to tune our inductors, our coils, like the old timers did. And the way they did it was by tuning the inductance and the measured resistance of that wire. See, there's a big difference between a resistor, you know, that we add to a circuit and the measured resistance in a coil. There's a difference, and we're going to talk about that in the next clip when I get the old chalkboard out. But you know, that's how they did it. You know, they tuned their inductors, and what I mean by that is they tuned the inductance by either adding more wire or changing the core, or, you know, they raised and lowered the inductance in a large window, right? You know, not a tiny window. If you have a tiny little coil, okay, you move a core in and out of it, it's going to change the inductance, but you need a bigger window to play with, right? And that's what they were doing. But they tune these things together, and really the guys from 100 years ago really were the masters at it, doing that and making motors sort of opposite as we do today. Our motors are made all wrong with that respect. We have very low inductance generators and motors, right? The inductors in there, in the motors and in our generators, very low inductance, right? So you'll see how that plays in to everything here in making a nice balanced machine. So what's happening there, right? What's that sweet spot? Well, if we're adding inductance and making changes and adding or subtracting measured resistance in an inductor, which is different from regular resistance, which we're going to see. If we're changing those things and it changes the sweet spot, then it tells us, you know, that sweet spot is due to reactance, right? And the changes that we see in our input and outputs are due to impedance changing with that reactance. And again, we're going to get more in depth there. This is just sort of touching on introduction to it, right? So resonance in an electrical circuit, right? Sure, it's a balance between capacitance and inductance. Now we're going to leave the capacitance out of this. We're just talking about inductive reactance here, right? Well, my demo is going to be a Bedini, and there is no capacitor involved. And the equations and math I'm about to show in the next clip are going to be dealing with just the inductive side. Know that there's a whole nother capacitive side as well to this video I'm even making, right? So this whole video here I'm making is, who knows how long it's going to turn out to be, but it's just scratching the surface, really. But the things I'm talking about can be done with even just the inductive side. And just to mention, Ed had variable inductors on his wall there at his castle. But, you know, this is what the sweet spot of a Bedini is. You know, that's reactance, inductive reactance to be specific. And that's what we're going to look at. And hopefully it's easier to understand with the Bedini. Now, this isn't a new idea that I'm sharing. I just recognize this and trying to make it easier to understand with the whole underlying concept, right? But a guy named Oliver Heaviside, you know, 100 years ago, came up with the term reactance and the idea of it, right? And studying it, and boy, you know, he developed the equations, I think. But truly one of the founding fathers of electrical knowledge, truth, right? Even though it's been clouded over the last 100 years. This guy, you know, I think maybe from what I read about him, maybe was a little jaded and angry at the world, you know, which is what happens, you know. Another reason why I'm sharing this, you know, people may be wondering, oh, why isn't he developing it or this or that, you know. I'm just not interested. I hate money. I hate the Queen. I'm probably a little bit like this guy, right? Maybe a bit jaded. I don't care. I know what's important in the world, and they're the things that we can't measure. Anyway, we're going to look, but what I wanted to say there, most importantly, is these ideas have been around. This isn't new. These ideas have been around. He knew 100 years ago, right? And wrote books and papers and did lectures and, you know, did way more than I'll ever do with this. You know, well, obviously, but so, you know, I'm not making speculations really in this video either. This is cold hard facts, right? So hopefully there's not a lot of people wanting to debate or inject some sort of negative, trying to find a mistake, you know. Oh, I'm human. I make mistakes. I misspeak. You know, but the meat of the sandwich here is factual and based in mathematics, which we're going to find out here in a minute. But next we're going to take a closer look at why reactance has been ignored as a good tool, right? A good tool for making motors and generators. We do the opposite, right? So next will be math. Well, we're going to look at equations and the relationships between reactance, the things involved, you know, inductance, resistance, measured resistance, impedance. We're going to look at Ohm's law and things like that. So the next clip's going to be the chalkboard. Off to the chalkboard. Okay, we're at the chalkboard. Everyone take your seats. Haha. Okay, so now we're going to take a little more in-depth look at the reactance, and impedance, and inductance, frequency. You may hear my dog breathing. It's because he's sort of next to the camera. Now, to start off with, basically what we're asking ourselves is, what exactly is happening, right? We were just talking about the Bedini and reactance and resonance. And resonance, really, I see now as just sort of another way to say reactance, because that's the way I see it now. Everything is, to me now, everything is inductance and reactance. And I mean everything. Oh, Dr. Fox, I'm looking in your direction. I think of your message that you sent me a while back quite often, and your talk of the human body and reactance and the balance. And we can see that everything in the creation is based on the same thing. Okay, so first, before we really get started, these are just equations. It gets deeper than this, but we're just going to look at the equations and the concept, right? And first, we need to look at what is impedance, because that's something that's involved here, right? We've heard that term before, probably, along with probably the term resistance. Resistance basically blocks current in a circuit, and a normal linear type resistor that we put in a circuit and use in our electronics, these are resistive to DC and AC currents, right? Both types of current. And there's no give and take with these types of resistors. They're just fixed resistance. It is what it is, right? Now, impedance, on the other hand, is another type of resistance, basically. And it occurs in AC circuits, alternating current circuits, but also pulsed DC circuits. And that's why we see it in the Bedini. And it's why a Bedini has a sweet spot, frankly. We tune the circuit to that sweet spot, which is taking advantage of impedance, which has to do with reactance, which we're going to see. But basically, impedance, this type of resistance in an AC or pulsed DC circuit, this type of resistance has like a give and take to it. It's like the way I like to think of it is like a rubber band. And oh, I have a little picture drawn here. This is supposedly a rubber band stretched between two posts, and you can put a force on the rubber band, and of course it wants to snap back, right? Well, an inductor wire is the same way, and this is what impedance is, right? There's a restriction to that force, sort of like resistance restricts current, and we're going to look at Ohm's law in a minute. But in an AC and DC circuit with a pulsed DC or an AC waveform, what happens is that wire sort of flexes like the rubber band, right? And there's give and take. And that's what impedance is. It's the resistance caused by that bouncy give and take in the wire. And we'll see that it's governed by reactance, right? The reactance is here in the equation. We're going to talk about that in a minute. And in my humble opinion, this give and take type resistance called impedance, really in itself and the nature of it, the nature of the reactance, the give and take, the reactance in that wire, I really should be calling it reactance. The give and take in that wire, that bouncy reactance, resistance, that really just in itself, that reactance shows that electricity is all about spin, and hopefully I'll be able to relate why I think that or why I see it that way. That's a whole nother video. This basically is how I see the atom, and spinning back and forth, or spinning with the alternating current and creating different fields, alternating fields, and I think that's what this give and take rubber band type reactance actually, I believe that's what's going on. And I think that in itself shows that, you know, maybe this is closer to the truth. Anyways, again, whole nother video there. I don't want to get too far off the main topic. Anyways, wanted to mention it. Oh, well, also the nature of this reactance and in itself, and the fact that we only see it in AC and DC, pulsed DC circuits, shows that that's best, right? We want that full waveform. We want that up and down, the positive and negative deflections, right, in the wave. Now a positive and negative pulse DC, I think, is going to be best, believe it or not. That's my opinion, whatever. But you can see how they're similar, and they really are. But a positive and negative pulse DC would be very good too for creating reactance, the AC. It shows that alternating poles on a motor, like I'm going to demonstrate here in a minute, my rotor has alternating poles on it, and it's a Bedini, but it has alternating poles, right? So it's pulsing only one side of a DC pulse, right, in the run wire on one half of the cycle. But the other half of the cycle, there's no pulse in the run wire, but the magnet going by pulses it, pulses that run wire, and gives us that rubber band kickback in the run wire, giving us reactance in a Bedini. And this, you know, you're going to see it more in a Bedini with alternating magnet poles, right? And that's what I'm going to show here in a minute in the demo. wanted to explain that. Hopefully that's clear, because that's very important. I've experimented with just more pure Bedini setups with all north facing out, and sure enough, that's what I saw. You know, I don't have numbers to quote you right now, but you know, less reactance, let's just say. Much less. So the alternating poles on your rotor with the Bedini with respect to reactance is best, because of the reason I just said. You know, we're pulsing that coil with one side, and then when the cycle finishes, it doesn't induce a pulse in the trigger, or you know, it doesn't induce the trigger pulsing the run wire, but the magnet passing by still makes that wire flex inside with reactance, creating impedance. So first, the reactance equation, right? X is the symbol for reactance. The subscript here, L, it means inductive reactance, right? There's also capacitive reactance, which would be XC. And it is the inverse of this equation, right? This is the equation for inductive reactance. Capacitive reactance would be 1 over 2 pi FL, right? So we're just talking about inductive reactance, right? But be aware that capacitive reactance is the inverse. And really, when you think about it, that only makes sense in the way a tank circuit works, you know. First our inductor pulses and then our capacitor pulses. So they really are the inverse. And the math shows us that. But I just wanted to mention that, the other equation. But we're just talking about inductive reactance, right? And the factors affecting inductive reactance basically are frequency and inductance, right? The 2 pi remains the same factoring every time, right? These are the two variables. So frequency is sort of a result, the work done with the Bedini style motor utilizing reactance, hopefully like we're going to see here in the next clip of the demo. But if we increase frequency here, you can see, or if we increase inductance, the result is going to be an increase in reactance, right? Inductive reactance. So this number would get better. If this number gets bigger or this number gets bigger, this number is going to get bigger. The total reactance, right? Inductance can be changed, right? We can change that by changing the inductor design characteristics, right? You'll have to get familiar with that. You'll want to be familiar with all these. I can't define everything in the video. It'd be hours and hours long, right? But we can change the inductance value by changing the inductor characteristics, whether it be by changing the shape or adding a core or whatever it be. We can change the inductance, and thereby that would change the resulting reactance, right? So now, changing the reactance, right, results in a changed impedance. And impedance is what blocks the current, right? It's like resistance. But the reactance is good, because the reactance results in work done, right? And you'll see, we can do work with, well, I'm going to say it, we can do work with no current input, right? I'm not going to show that here. I can't yet. I need wire, you know, other than the scraps I've been using. But we can block current and still do work, I guess is what I'm trying to say. But changing the reactance is going to result in a changing impedance, and that is because reactance is part of the things that make up impedance, right? We have the measured, this is, the R represents resistance in the wire, the measured resistance, right? when you put your ohm meter on your coil and you measure the resistance, that's what we're talking about here. And this is the inductive reactance that we just talked about over here, which was derived from frequency and inductance. Right? So if we change the reactance, you can see how it's going to change impedance. If you increase reactance, you're just like over here, the relationship is such that we're going to also increase the resulting impedance. And also if we increase the resistance, the measured resistance in the coil, we're going to end up increasing impedance, right? So although inductance and frequency aren't directly part of this equation, they really are through reactance, right? So that brings us to Ohm's law, and talking about it in a way of blocking current, but in a different way, right, with impedance. Now Ohm's law traditionally with DC would be I equals, or current equals voltage over resistance, right? But Ohm's law also states that we can substitute the resistance with impedance if we're talking about an AC inductor, right? These are all things you can look up, Google, all over. If you go to university to learn these things, this is what they're going to tell you, you know. This isn't made up or anything like that. Nothing's changed from the norm either. So our resulting current, right, can be derived from the voltage input and the impedance that we've calculated from our coil, right, from the variables that we have of the coil. And an increase in impedance, right, you can see that this, if this denominator increases, then our resulting current is going to decrease, right? So if Z becomes bigger, right, impedance becomes bigger, let's say voltage is 1, we're going to have 1 over a larger number, which is a smaller fraction, right? And you can see current decreases. So basically what this, and this is the reactive power calculations basically that people do. The gentleman I mentioned earlier that was at the Tesla Tech Conference, this is basically what he was doing, right? He just needs to make an inductor that suits, that gives him a better reactance balanced with the resistance, blocking the current, but still doing work. And that's the next clip. I'm going to show a Bedini motor, pulse motor. It utilizes a Bedini circuit, but that's the only thing Bedini about it. And you'll see that when we go to the next clip. And I think that demonstrates what I'm wanting to show best. So we're going to go do, with the next clip is going to be that. One last thing, this is my LCR meter. Someone sent me that in the past, and I really thank them again for that. This is the most important tool in your bag if you're doing these things. If you don't have one, get one. Most important tool in the bag. You can't see them all. I've got 2 stacks here of microwave oven secondary windings. I've got 18 total that actually are continuous and usable, but I have a stack of unusable ones too that didn't quite live through the, they didn't survive the operation. They died on the operating table. And anyone who knows, you know, how it's like taking one of these off a microwave oven transformer, I'm just maybe trying to give a hint at a lot of the work I've been doing. I've got 18 of them, and I've got a bunch. I did more than that, but I've got 18 that survived the operation, and you know, pretty good average actually. 1 in 4 didn't live through it. But anyways, just trying to relate where I've been and what I've been doing. But next is a demo of the motor talking about all these things. Okay, time for a demo. I mentioned before I'm going to be showing a Bedini. The circuit, this right here, it's exactly like a video I made 1 or 2 videos ago showing how to make a Bedini circuit yourself. It's exactly like that. So I made a couple of those for this demo. That's the only thing really Bedini about this. You know, the core and the coils are not. Bedini used bifilar wound coils, and these are separate coils. They are secondary windings from a microwave oven transformer. Like I mentioned before, these are the 2 E-cores strapped together. The E-cores from those microwave oven transformers. They're strapped together, polished nicely, so there's a nice magnetic connection. And then there's a core coming off those, pointing towards the rotor, which is the bottoms. There's bottoms on these cores, and you grind the welds off, one on the top, one on the bottom, and the bottom comes off, right? Well, I used the bottom pieces to make this part of the core, right? That goes through the centers of the coils. The rotor is made out of microwave oven magnets. It's 2 microwave oven magnets, alternating poles, north and south, so there's a full cycle going there. Magnetic cycle. It's all garbage, right? The bearings are garbage. There were those rollerblade bearings that I like to use in my videos. They're okay, but they're what you would call, and I don't want to talk over anyone's head scientifically here, but they're what you would call ultra crappy. Anyways, you can do the ear test when it comes to bearings, right? You can do it right here in the video. What are your ears telling you, right? Crappy. It could be way better. Some sort of maglev or frictionless thing here is going to result in a higher frequency. But I have meters here. There's just input to this circuit. There is no output. There is no wire on the output. I'm not going to get into that other than to say there is an output that we're not even talking about. The light's flashing here. You can put a capacitor on there, no problem. You can put a battery on the output, but it has to be a large, deep cell battery that measures, well, for this right here, what I'm doing, the output needs to be on a battery that measures 2 mega ohms at least, right? So we're talking over 100 amp hour battery. And it won't affect the performance, right? Or what's being happening here in the input. So all we have is an input wire. It's hooked to a wall transformer, and it has a rectifier in it. So I have DC output, and it's at a constant 12 volts. I have my ammeter in series with the negative pole. Here, there's a wire just going straight to the positive pole. And my ammeter is in series with the negative. And right, this setup right here is drawing 15 milliamps at 12 volts, right? And I just tried to see if this works. I hope you can see this. I'm just going to move it a little bit because I know there's a little bit of reflection, but we've got 800 RPM, right? So with the semi-crappy bearings and whatnot, we're pushing at 800 RPM, which is pretty good, right? It's doing a fair amount of work. Now, this by far is not my best setup. I'm using this setup, and we'll see in a minute, because I have another one. I've made identical to this one. The core is identical, and the winding, the core is identical. Weighs, I mean, to the gram, exactly the same shaping, everything. But the windings on the other one are just slightly different. But for all intensive purposes, they're the same. There's two as close together as I could get them, right? With respect to the windings, this winding right here is 1.8 Henrys inductance. The one I'm going to show in a minute, and they're going to work together, and we're going to see something cool. But this one's 1.8 Henrys, 1.80 Henrys, and the other one is 1.79 Henrys. So they're very, very, very close to the same. And this coil here, the run wire I'm talking about, this is the run winding, this is the trigger winding. And they're separate, but they're together on the same core, so they're coupled together inductively, right? We don't necessarily need to have a bifilar winding, and I'll talk about that after. We're going to talk about Tesla and Ed and a whole bunch of stuff. This ain't over. But I have another one made, and we're going to see them work together, and that's going to show something cool. But what I want to talk about right here is, okay, so we're using 15 milliamps at 12 volts. I don't even remember what that works out to wattage wise, but well, as we've seen already, we can't do a straight wattage calculation anymore with our Bedinis, especially if we have them tuned, the iron and the copper. We need to take into consideration reactance, just like we do with AC circuits, right? But what I want to point out here is that I'm doing a fair amount of work, right, for very little input. And again, I can go way lower than this. We're going to see an example of lower than this. After we have two on, the two identical ones working together, then what I'm going to do is I'm going to take both run windings and put them on this core with this trigger winding, and we'll have the two run windings on one core in series, which jacks the inductance up, and we'll see what happens with the speed and the input. But this run winding is 97 ohms when measured with an ohm meter. The matching one is going to be 99 ohms, right? They both, I've tested them both thoroughly, and they're both at the same distance from the magnets. The cores are. They perform almost identically the same, although there are very subtle differences, and there are very, very subtle differences, but for all intensive purposes they're the same for the scraps I use, right? So what I want to say here is that the reason I'm able to do this is because I've added a lot of iron. This is very atypical for a Bedini core, right? It's a lot of iron. Basically filling those windings, right? And I'll pick up the camera and have a closer look at it here in a second. But, you know, this is a lot of iron. I think it's 16 pounds. 16 and a half pounds total. I weighed all the individual components and then added them together. And a little bit of wire, this is where my needing wire comes in. I know what gauge and how much and how many windings I need. But I'm making a vid to show you guys, you know, with the stuff I've been using before I go and do that. So you can do it too. So what I've done is I've balanced the reactance like we talked about in the last clip, right? So I have my inductance I've jacked up with this iron, right? This coil itself, you know, has good inductance value, but when I add this core to it, it really jacks it up, right? And it has a very good resistance value when measured. 97 ohms is nothing to sneeze at either when it comes to a Bedini. So, you know, sort of new ways to look at things and using things and getting results, right? So what I want to show next is, and this is balancing reactance and resistance to get work done for no current. That's what I'm trying to do. And again, by far, this is not my best setup. I've seen people do, you know, just as well on YouTube, or, you know, one or two people. And that's great, you know, but it can go lower. We'll see that in a couple clips. And if I were to have, when I get wire I need, you know, this is going to go to 0, and it's not going to stop at 0. Believe it or not, when it's all said and done, this won't stop at 0. It'll actually start going into the negative values. And what that means is that this machine will be running itself and throwing a current out of the input wire, right? And then at that point, all you need to do is put a capacitor on the input, right, with a voltage in it, and it'll basically be running on just voltage. The voltage of the capacitor is what will be running it, and also throwing a current this way, right? So what'll happen is, in my guesstimation, that because there's a current coming this way as well, it's not using any, it's giving current. So what'll happen is the voltage will rise in this capacitor, and as voltage rises in a motor, we know that the motor's going to accelerate. And I'm wondering if it's going to have some sort of breakaway speed with the capacitor on it, where it'll go faster, so it'll throw more out, throw the voltage up higher, make it go faster, you know, and break away until it goes too fast for what we have there. That's a good problem if we run into that. It really seems that's what's going to happen. And I'll show you in the third clip here of the demos why. Well, I mean, I know it can go into the negative value. I'll show you in the final setup. I'm going to put a little cord on here and get the rotor going faster than what this is tuned for, and it will be negative until it slows down enough, and you'll see it'll go to 0 and then it'll come up. I think, well, we'll see. You'll see what I'm talking about. So again, balancing inductance, resistance, or in other words, impedance, or the reactance affecting the impedance, balancing the resistance with the reactance, that's impedance, right? And getting good work done, right? So next, we're going to set up another one just like this, tuned just the same. Oh, by the way, there's 22,000 ohms on the base of this resistor in series with the trigger winding. So be prepared to, and that value depends on is dependent on the inductance value of the trigger winding. And this reminds me of something I really wanted to mention, is that my intent was, and I wanted to crunch the numbers so that I could show from the chalkboard when we talked about it, punch in these values, right? We could punch in 12 volts, we know that, and we could put that in Ohm's law, right? When we're trying to find the final current. But we would know the frequency, right? It's 800 RPM, and with just two opposite poles on here, that's one revolution is one cycle, right? So divided by 60, I think that comes to about 13 hertz. I know the inductance values, right? But, and I wanted to crunch the numbers and show you, but it's not quite as easy with this setup to just plug these values into those equations. And that's because in the Bedini setup we have the bifilar, or the coupled inductors, and what ends up happening in this situation is that we have two reactances happening here, and they have to be calculated separately, I think, and added together. Why not? But I didn't want to, I had it all worked out, but I didn't want to confuse things, right? With a generator setup or anything else, yeah, you just plug these values into those equations, and you know, you're going to come up with your current, right? Or if you're working backwards and you want to know what your frequency is going to be, bing, you know that, right? So this is what I've done here to the best of my ability with the garbage I have. Now I have a basically identical setup here. I'm going to bring out same tuning, same everything, same distance from the magnets, and we're going to see what happens when we put them together. So we know this one goes 800 RPM, 15 milliamps at 12 volts, right? So I'm going to hook the other one up, and I'll be right back. Okay, demo clip 2. As we just discussed, this is the same core and coil setup that you just saw. I have an identical one for all intents and purposes. Very, very closely matched, and they're going to work together. Again, I have the ammeter in series with the negative pole. We have a wire just going straight to the terminals here. The input wire, again, is just hooked to the terminals. Obviously have another one coming from the other coil, and again the ammeter and the straight wired. So anyways, they're in parallel. The two Bedini circuits are in parallel with the input. We have the ammeter, voltmeter. I don't have it on right now. I want to just give you a little closer look at the core and coils. Again, that's the E cores from microwave oven transformers, and those are the secondary windings, right? And that, I can't get around here. That core is made out of the bottoms of those E cores. Right? They're taped together and polished smooth where the connections are, and zip tied up. And this one's just the same. They're the same distance from the magnets, right? Everything's the same. And again, they weigh the same. There's only 1 or 2 ohms discrepancy between the ohmage resistance of the run coils. There's a slight difference in the ohmage and inductance of the trigger windings. They're pretty close, not as close as the run windings. Run windings are almost the same. And again, that trigger inductance is what determines your resistance value on your transistor base. So anyway, oh, and the rotor is those microwave oven magnets. And there is a one roller blade bearing up at the top, and there's actually two at the bottom. And by the way, I mean, those are horizontal bearings being used in a vertical position too, so it's like I'm not even using them properly. But it gives off a little noise. So anyways, here we go. We'll get her spinning. It picks up speed nicely. Oh. Pretty quickly it gets up to speed. So again, the constant 12 volt input, right? That doesn't change. Now we're going over 900 RPM. Again, we have two identical setups working together, so that's not surprising. But the sort of surprising thing is that our input current is now only 20, or it's only 20 milliamps. Now we'd think that usually when we put two Bedini circuits, systems, in parallel, right? Basically what happens is you add together what the inputs are, and that's what your new input's going to be, which is basically going to be both added together, right? Well, that's with the normal type Bedini core, right, and coil. With the tuned setup, what happens is the Bedini becomes sort of opposite the normal setup. So when reactance is tuned via copper and iron, right, we've tuned the reactance and thereby the impedance blocking the current. But when we do that, the Bedini behaves differently. It behaves oppositely. So when we increase the RPMs or increase the frequency now, what happens is we reduce the current input. Now with the normal Bedini tuned system, right, if you put friction on the axle and slow it down, your current input goes down, which is the opposite of a normal motor, right? Well, in this, it's the same as a normal motor, where in the sense of if I put friction on this axle, what's going to happen is this current's going to go up, right? And the reason is because the frequency is going down, right? As we saw with those equations, you drop the frequency, which means you're dropping reactance. You drop reactance, you thereby also drop impedance. And if you're dropping impedance due to Ohm's law, tells us if you drop the impedance, what happens is you increase your current, right? Wow, did I get it? Yeah. Drop the impedance. Your impedance drops. Your current's going to rise, right? When you put pressure on it. Sorry, I misspoke. And I just watched a couple of those clips I made, and I misspoke a couple times. My apologies. Anyways, my point being that now with this Bedini balanced reactance system, now that we increase the frequency, right, what's happening is our circuits are becoming more efficient. And again, back to those back to those equations, we increase the frequency, means we're increasing reactance. If we increase reactance, we're increasing impedance. And if we increase impedance, we're decreasing current, right? So the higher frequency is good for this circuit because it makes it run even more efficiently. Now we saw this in the last clip, that this on its own pushed the wheel 800 RPM and used 15 milliamp, or was it 15? 15 milliamps. So now I have an identical one working with it, tuned the same efficiency. I tested them separately, you know, same thing. Pushed 800, used 15 milliamps, same thing. So now working together, obviously they make the wheel go faster, right? Now we're going a little bit over 900 RPM. But what in effect that's done now is that because the frequency has increased, both of these circuits have gotten more efficient, right? So if we take this 20 milliamps that we're running at now, we've only increased by 5 milliamps from just one running by itself, right? So we take that 20 milliamps and we divide it by 2. So now we can estimate that each one individually now is running it on 10 milliamps, right? Average. So our efficiency has increased, you know, by a third. I think that's right. Right? So our efficiency has increased quite a bit, right? And our rotor's going faster. We have more torque, more speed. And we've gained efficiency. Now again, this isn't my prime setup that I have, even with the scraps that I have been using, right? So again, why is it important, right? Why is it important that it behaves differently when we've tuned the iron and the copper, the reactance and the impedance? It's important because it's most important. And it's because the two working together increases frequency, but makes both circuits run more efficiently, right? And again, like we mentioned before, eventually 0 could be achieved, and actually less than 0 could be achieved. We'll get a sort of a glimpse at that in the next clip. And all the while, more and more and more and more work being done, right? Can you imagine, let's say a rotor 3 times as long as this with a couple more of these on there, which really wouldn't change performance very much. And say 6 around here, and then another level with another 6 around there. All tuned exactly the same, right? All tuned exactly the same. And then another 6 on the next level. And then have even that third level, like I was saying, and have another 6. You know, like I said, I'm not going to make any claims here. And again, this isn't my project, and this isn't my machine, per se. But, you know, it doesn't take too much imagination, well, or math, you know, if you want to be precise, to see where this is going, right? It's joyous, really. And this is what I've been doing. Now you hopefully can be doing it too. So anyways, next what I want to do is, like I mentioned before, is I'm going to take this core off, and I'm going to take this run winding here and put it on this one in series with this run winding. So essentially what we're going to be doing is doubling the resistance and actually tripling the inductance because of the behavior characteristics of that. And again, I'm going to talk about that when I talk about Tesla. But and we'll see the effect it has on, you know, obviously impedance, but what we use, and it's going to go a little slower, you know, but not that much slower. Alright, so here we go, clip number 3. Okay, third demo. So again, what I've done now is I've taken the run winding off of the other coil setup, core setup, and I've added it to here. They're in it's in series with this run winding. So now there's 196 ohms on the run winding. Those two windings are in series, so there's 196 ohms there. The inductance is 6.01 henries. And again, we're going to talk a little bit more about that kind of why it tripled, and you know, the winding arrangement, things like that. Same trigger coil. So same resistance on the transistor, right? We still have the light blinking. So now we're down to 5 milliamps. The speed is down. Again, we're at this fixed 12 volt voltage. It's a little slower, just under 500 RPM. Just under 500 RPM. And there you go. Now, I just want to say, so now what we've done, we've increased the resistance in the run winding. The core has stayed the same, right? The inductance has tripled. It's up to 6 henries now. So we've increased the inductance, right? We've increased the resistance of these windings. So those two things together give us impedance, right? So what we've really done is really increased impedance, and we've driven it down to 5 milliamps. We're still driving the semi-crappy rotor. 500 RPM, just under 500 RPM at 12 volts, right? And it still all conforms to those equations I showed, and just a little more complicated than just punching them in for a Bedini with the multiple reactances going on here to get the numbers to work, and I don't want to get it overcomplicated. But this is what's going on, right? This is what's going on. This shows it. It's a Bedini, but it's a different Bedini setup here, right? Which has changed things. Well, we just lost a connection somewhere there for a second. Anyways, time to wrap up this segment. Next, I'm going to be coming and talking about Ed and Tesla, and how this relates to Ed though first is what I want to do. I've got a bad connection there somewhere. Anyways, next we're going to talk about Ed and how this reactance and impedance and inductance and all of it relates to his setup. And I was looking at the clips already, and I think it's over an hour already, so whatever, I don't care if you don't care. Anywho, let's talk about Ed. Okay, oops, forgot the overspeed demo here I want to show you. So I still have the run coils in series, 196 ohms of measured resistance at 6 henries. Inductance, right? So it's giving us that reactance, which is blocking current. I think we're at 5 milliamps here with this at 12 volts, pushing it just under 500 RPM, right? So what I've got set up here is I have a little ripcord up here on the top. And what I'm going to do is I'm going to give that a yank. Pardon me. I'm going to give that a yank and get it going way over speed, right? So it's going to, the rotor's going to be turning really fast. Like, it's going to start out over 1,000 RPM. I'm going to flip the switch on, and I'm going to try and grab the tachometer real fast and get it pointed showing a reading. And what I want you to watch is when it starts out and it's going at a higher frequency, you're going to see the ammeter here is going to show a negative value, which means when it's showing a negative value, what it means is that current is going this way, right? It's not going this way, it's going this way. So it's throwing off a current. But as the frequency reduces and the negative value approaches zero, what we want to notice at the 0 point before it starts going into positive numbers, and then eventually it's going to stop at, it's going to raise in the positive values up to 5 milliamps, right? Then it's going to run at just under 500 RPM. But what we want to notice when I give it a rip over speed, we'll see the negative value. I think it goes to 3 milliamps negative. But as it approaches the 0, when it's at the 0 point, we want to look at what the RPM value is. Now this is going to be a rough estimate. This thing takes readings, I don't know, every second or half second, I don't really know. But we're going to get kind of a glimpse at what the RPM or frequency this system tuning requires to be 0. So in other words, how many of these would I need to get it going that RPM to make all the circuits running so efficiently they're 0, right? We'll see an estimate of what the speed is, keeping in mind that it went just under 500 RPM, right? So here we go. We're going to give this a try. I'm going to give it a rip and we're going to see. I'm going to grab the tachometer and look at it, and as this slows down, this is going to come back towards 0 from the negative values towards 0, and when it's at 0, we want to look at what the RPM reading is. So here we go. 14 milliamps. So here we go, 0, it read 722 RPM, right? And now it's going to settle at that. I think I broke something. I think I pulled my rotor out of position. I spun it way too fast. It kind of screwed up my rotor, I think. So we're going a little slower, and I can actually see there's a problem there with the rotor. Anyways, this should be going just under 500 RPM, where it's settling at 5 milliamps. Now when it's slowed down, and I say that because we just saw that in the last video, right? I just demonstrated that. And we had 5 milliamps at 492 or 3 RPM. And I've broken it. This happens every day, and I want to hang myself with this wire sometimes. But anyway, keeping that in mind, the value here, when this was at 0, when the frequency was dropping, the value when this was 0, the RPM value reading was 722. So we get a little glimpse at, in the last clip we saw, this setup in this tuning drove this rotor just under 500 RPM at 5 milliamps, right? So I put it way over speed, screwed up my rotor, which I have to fix now. But put it over speed, and as it came out of the negative values back to 0, when it was at 0, the tachometer read 722 RPM. So my point in doing all this and saying that is that This circuit right here, setup, requires somewhere near 722 RPM for it to operate at 0 milliamps. Literally 0, right? So it pushes it just under 500, 494 RPM, something like that, on its own, right? So if I keep adding these, it's going to go faster and faster, and it needs to reach that somewhere near that 722. All very interesting. All numbers you can crunch if you're going to get and try this, and these are all numbers you can crunch and very interesting things. I can't wait to order some wire so I can start making some new run windings, and have something cool to show you, even cooler. So there you go. Oops, forgot. I wanted to show you that overspeed. Sorry that I messed up my axle in the process, and it settled just a little lower, like 480 RPM instead of 490 something. It's out of kilter. But anyways, we saw that the overspeed drives it into the negative values, and when it was zeros, 722 RPM for this setup. Now individually with this single winding on there, just like the other one, you know, when I had one run winding on here, those values would all be different, but all percentage wise in balance, right? Definitely. There we go. There's the demos. Now we're going to talk about Ed. Here we go. Okay, so we saw some demos that I was able to put together. Hopefully that puts it into perspective a little bit. That's a glimpse at what's possible, right? Using what I have here. Now I'm going to be ordering wire. I know exactly what I need, how to apply it. But the most important thing is I know why. You know, I know why now, after doing all the tests and reading and learning that I've done, specifically over the past recent time. I know why now, and that's most important. And it's just a matter of just making it happen. And again, I just want to say, you know, I showed it with the Bedini, how to tame it, and but this applies to all motors and generators, and we don't use reactance in our motors and generators, and we need to. It's not a big scary thing, right? I just want to show this page again. If you Google inductive reactance, you'll find pages, informative pages like this explaining it, right? And it goes deeper than I've touched on. You know, we can talk about phasor diagrams and lagging or leading degree angles, but you know, I don't want to get that's another video, right? Or two, or whatever. Oh, I'm such a nerd. This is all such fun stuff to me. But when I'm done making this video, I'm going to lay down and sleep for a couple days. Just making this video has taken me a couple days, and it's been a lot of work. I was just looking at, this is day 2. I was looking at the clips I've done so far, and it's kind of a saga, I see. And I would say sorry, but I'm not going to, due to the content I've got here. I've just got to show it this way. And I want to share it before, you know, I order wire. I just don't have the resources. And me and my buddy were laughing about it not too long ago. He was over here, and he saw me working on it, and we were laughing at my tools and my soldering iron. And, you know, I'm the guy perhaps to carry the ball and figure this shit out. But, you know, I'm perfectly willing to hand this off. Always have been, you know. But I want to show you all one big, I got to show it this way. I can't upload a bunch of 10-minute videos about this. Not in the beginning. Even if it is long, and even if it is just touching the surface of it, you know, this is the way I got to do it, as I see it. But now I want to touch on Ed Leedskalnin, his setup there at Coral Castle, and he had his wheel, and you know, a lot of us have studied it, but basically his PMH here, and this is going to be a whole nother video too. I just want to touch on the relationships of what we've talked about to Ed in his setup. But his PMH here, and I've studied this in the past and made lots of videos. I didn't know why thoroughly back then what was going on. I knew it was an inductive reaction, you know, and I called it inductive reactance, you know. But I didn't know thoroughly why. Now I do. And how to make a transformer and all of it, and how phi relates and spin and all of it, you know. I'm not saying I know everything. Hopefully you don't get that impression here, but you know, I do know thoroughly now. But anyways, another video I want to make is showing the inductance of Ed's setup. His PMH here, what it really does is jacks inductance up, and as you move these coils up and down these prongs, you know, that's going to change. In another video I want to show that. But this center area that we kind of focused on, I have a video in the past about it, this null point. You can add iron here and increase the inductance of your inductors here. So that's what he was doing, right? And I made the video in the past about it, and I had a little diagram, you know, that I showed. Now, disregard the bucking coils and the homopolar and all that, but for now. But basically that's what I was showing, you know, hooking the iron, and that's what we see in the pictures, right, to his mass of iron, right? But simply just hooking a mass of iron to that point in those prongs of his PMH is going to jack inductance up, which is going to increase reactance, as we saw. He would be able to have a nice heavier gauge wire than I'm able to show, of resistance to balance with that jacked up reactance, and he would be able to generate electricity without lens. Due to the, you know, if he had a phasor diagram of what Ed was doing, we'd see that he's using timing and inductance to his advantage, right? We talk about resonance and reactance, you know, and when we talk about resonance, we talk about frequency mostly, and oh, it's all about frequency, it's all about frequency. Well, frequency is a big part of it, right? As we saw from the equations, it's half of it, but or a third, or however you want to look at it. But there's more to what we call resonance than just frequency, right? It's inductance involved. And resistance, right? It's a dance. I like to think of it sometimes. But another thing quickly I want to point out here about, so, you know, he obviously has, this is a alternating pole magnetic wheel, right? And he's got something next to it that obviously is iron, right? So we know he's generating electricity here. Now, I don't think he's got a pulse motor set up here. I really don't. And there's a couple reasons why. But we see here, and have shown in the past, you know, he's hooking to that point, right? Here's alternating poles, right? And he's jacking up the inductance, and he's using reactance to his advantage. He's the master of reactance, right? And his setup proves it. And the mass of iron And I've done this, and I want to show it in videos to come. Literally show it. You know, I've draped chains all over my setup over there. And it's fascinating, right? But you have to balance the resistance with it. You know, it's easy, just like he said, it's easy. It's just in knowing how. And I mean, he's a master making it out of this stuff. I just so wish that I was able to do it with the scraps that I have. That's been my goal here recently, in recent months. I'm stubborn, and that's, you know, that's what I wanted to do, but it's just not doable with what I have, right? So anyways, that's what I'm going to be working on. But I wanted to point that out. Now, another big reason why I think he's generating electricity rather than driving the wheel with this setup here, now he has two positions, right, is because I've looked, and other pictures reveal this better, but this right here in this picture, this is an electric motor, right? And the way my mind sees it, it's there for a reason, right? The way my mind sees it is this can be tipped down, and on top of the wheel here he has a large gear, right? And the cogs can be put on the end of the rotor that mesh with the gear here, and this can be used to drive the wheel. Now, if there's no lensing on the wheel, once this mass gets spinning, it's not going to be a drag on this motor, right? And if he's able to produce more electricity than it consumes, then, you know, that's what he's got. But that's sort of what I see here. And if you look at other pictures, this is what you see. There's an electric motor here right next to his wheel. And the gear on the top. Everything has a purpose in what he's built. So, and if you look closely in other pictures at this gear on the top, you can see the cement is worn in between those gear nubs, those teeth. Anyways, just wanted to touch on that too. So this is what it looks like he's doing. You know, now we're at the point we can really look at this and say, you know, he's using inductance to increase reactance to change his phasor diagram of the electrical system that he's got going on here, so that there is no lensing on the generator coils. So wanted to mention that, and again, I'm going to have a video of Ed's setup as it relates to this. I could make another long video. It won't be this long, but so I think that's what he was doing. I wanted to touch on that in this clip. There's lots of others. There's lots of other things too that I can touch on. This video can be hours and hours long, right? It's going to be long enough as it is. But just realize that there's a lot backing what I say. It's not fantasy in any way. And if you come to the comment box looking for an argument, you know, you obviously don't realize the uphill battle you're against. So, and I don't argue anymore. I just delete. Anyways, hopefully someone can find the humor in that that knows me. Okay, so next, one more clip here of other applications. I want to talk about Tesla and Daniel McFarland Cook and Stan Meyer and a few other things. So that's coming next. Okay, second to last clip, I want to talk about other applications and past applications of these ideas people have had. Now again, Oliver Heaviside wrote extensively about it and explicitly about it, right? But actual devices that utilize it, have sort of been clouded and suppressed, right, from mainstream thinking for 100 years. And it's this inductive reactance, impedance, that relationship that can be used to make better motors and generators, right? Our motors and generators they have iron in them, right? Great, but the windings in them have such low inductance that they don't use inductive reactance to their advantage, right? Something we need to do. I demoed the Bedini. It's a motor. It's trying to make a motor run itself like that, like I've been trying to do. Basically, hopefully, the end result will be a motor running itself purely off the potential from a capacitor, right? No current, just running off the potential. That's probably the hardest embodiment of this idea, right? The way I see it, other applications would be easier. For example, like a solid state application where you'd be able to vary the frequency yourself, right? In the example I showed, and the example I'm working with has a rotor with magnets on it. And Ed, same thing, it's dependent on the speed of the rotor, right? Well, with the solid state device, you could increase that frequency, right? Just like we increase inductance, and it's going to increase reactance. Now, also, I want to say that last clip about Ed, I wanted to mention that in his workroom there, they have his tools on display on a board, and he has 4 variable capacitors on there. I wanted to mention, I've noticed that in the past, and it seems pretty apparent that he's also knows how to harness capacitive reactance, right? He's probably using them together, which, from the math and the equations, we can see that's probably the best way, right? Seeing as though the capacitive side and the inductive side are the things balancing. But just wanted to mention that, the guy has got a lot going on there. Very, 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 very impressive. Very impressive what he did there. So, we just wanted to say a little bit of that and talked about Ed and whatnot. So now I want to talk about other applications and past applications. The first guy I want to touch on is this fella named John Christie. Just touch on this. Maybe people have seen this guy's video of this guy out there. News reports have been done about him. He's an Australian man who has, what they report on, a free energy device, right? It runs itself, puts out kilowatts of power. But in that video, if you watch it, I've left links for it in the past. It's not too hard to find. His name is John Christie. They show his device a little bit in that video, and you can see, coils around it, and I just know that this thing that I've shown you is what he has learned to harness, right? And he's doing it in a very similar way, right, as what I showed. Very, very interesting to look at and think about in light of what we've talked about here in this video. So, the first person I want to talk about is Nick Tesla. I've read so many of his patents, and, before I had a more complete understanding. And some of his patents, that come to mind quickly when thinking about this subject, is a patent here. He's got a couple of them. It's not just this one. This is patent 487796. And, but anyways, I wanted to show, it's a ring of iron, right? and, you know, with prongs coming off with coils on them, inductors. And what these coils are, these are bifilar coils, right? I don't know if anyone's ever noticed that. These are bifilar coils, just like the example I showed, had 2 windings on them. These 2 windings are important. And the way he has them wired, and you can see, you know, in between these prongs, like here's a PMH, basically. Here's a PMH between those two, a PMH between those two, right? So this is going to give a good inductance, right? Now, depending on the wire he uses, you know, and having it wired this way, you know, this is what he was doing. If you read his patents again, you know, you'll find, and it's more than once, I can't quote exactly right now, but more than once in his patents he says, you know, he's describing how it works and what it's doing, and he says, you know, this sort of thing to the effect that, you know, it's contingent on the fact that you know how to make the best transformer, right? He says that more, you know, in more than one patent. Well, this idea of reactance is exactly what he's getting at, right? This is really a funky monkey right here. I just kind of want to look at the bifilar patent, his patent for coil for electromagnets. A lot of us are familiar with this, right? The pancake, done tests with pancake coils and this and that. Well, just to mention that, and this again is another whole video I can make, it doesn't need to be in the pancake shape. You can have an inductor, you can take your Bedini bifilar and wire it in this fashion, and you're going to get the same effect. Now the pancake shape is, this is the best inductive shape, right? Flat, you know, like this. If you go study the characteristics affecting inductance of, you know, an inductor, you know, the shape and design characteristics, you'll find this is the best shape for inductance. Well, what this wiring arrangement does is it jacks up the inductance. And just like I showed in my example with the Bedini, when I showed both of those run wires together on the same core in series, that's what I was doing. Basically this, right? Those 2 coils were in series. Now they're not wound tight together in a bifilar fashion, but they don't need to be, right? But this wiring arrangement jacks up the inductance, and there are a few videos out there on YouTube about that, but I want to make a video purely about just this, right? So what that shows really is that Tesla, through this picture in his patent, he's talking to us and he's saying it's all about inductance, right? It's all about inductance. And you put these pieces together, and you'll have a fascinating machine. And the way he words that is really good in different ways. Ed 2. And then you do the experiments and you will see. Nothing could be truer. Nothing could be more true. So it doesn't need to be in the pancake shape to get the inductive benefits, right? You can take a pretty normal shaped inductor, bifilar inductor, and wire it this way and get, you know, the same effects. Now this shape is going to give you the best effect that way, inductive effect. But to have, like, say, a normal inductor, shaped bifilar inductor wired this way is going to be pretty damn close to this, you know, the same effectiveness. It's going to be on the high end of effectiveness. Less than, say, if it was a pancake, all that wire in a pancake. But still getting that effect very good. So it doesn't need to be in that pancake shape, and Tesla's talking to us here, as he does in probably most all of his patents, talks to us and we don't even know it. So, you know, he's talking to us. A lot of these guys are. The next one I want to talk about, Stan Meyer. A lot of us are familiar with him. I have 0 videos about HHO, although I've made HHO generators in the past in my garage, and you know, had a lot of fun with that. Actually, that was when I very first started to make videos, and I made a welder, and then I made a couple HHO generators, and then I got into the Bedini stuff and started making videos. But I know a little bit about it, and one of the more popular videos of Stan Meyer on YouTube is very similar to this picture right here I have, where he's turning the knob on his controller here, and the video shows that the current is going down as he's turning the knob, and the production is going up, right? Well, does that sound familiar? Right? Just like the Bedini reactance, right? We tune the circuit and tune the current down and get more work done, right? It's the same thing. You know, we can look at it that simply and say, wow, it's very, very similar and the same, right? Well, it's because of the reactance, right? Mr. Meyer was also a master of reactance. All of these guys are. Tesla included. Maybe the headmaster. So he's getting the same effect. Now we can look at his circuit, right? And he even calls it, where's my cursor? He even calls it a resonant charging choke, right? Well, we've talked about resonance and reactance and how they're sort of one and the same, right? Well, he knew that, right? He knew that. So this is what he's doing. And I'd love to see a picture of his inductor, right? If there's one out there, I haven't seen it, and I'd be curious to see it, right? I bet you it's a good size, and I bet you it's in tune. Resistance-wise, with respect to the wire, and also with respect to the inductance of the winding. Now also his fuel cell here is a capacitor. So he's also got probably a capacitive reactance going on. So he's balanced that as well. Very interesting. Very, very, very interesting. His tuning knob, I believe, would be over here on this side. And I think. Anyways, again, I'm seeing the same thing. And we can look at this and see what he does in that little video. And he's doing it here, right? He's turning the current down and he's getting more work done. Right? Just like the Bedini reactance. Just like it. Just like it. You know, I would love to see his inductor. You know, I'm sure it's got a certain amount of iron and a certain amount of copper, right? A certain amount of windings, a certain inductance, a certain resistance. This is the key, right? Now making a, like say a 3-inch inductor and putting a 3-inch core into it, pardon my dog, he's having a, lay down. He loves me making videos. So, oh my goodness. So what he's done here is he's manipulating reactance, right? This is, I'd love to see his inductor. I bet it's a good size. So moving on, the next guy, Daniel McFarland Cook, came up with something called the electromagnetic battery, right? He's made a battery, apparently, right? And a lot of us have looked into this and wondered and tried to understand. He's made a battery out of copper and iron, right? Well, okay, well, he gets an oscillation going or something, and we've tried to understand. Well, in his patent, I've read it in the past a couple times. In his patent, he literally explains you need to put miles and miles of wire on these inductors, right? Well, what's that going to do? You know, whatever the gauge is, really. I mean, not really, but, you know, miles and miles and miles of wire is going to increase the inductance. It's going to increase the resistance of the wire, you know, depending on, again, what the wire gauge is and how many miles he puts on there. But, okay, so now I see he's doing the same thing, right? And again, he's got two windings, right? Sort of a bifilar arrangement. Sort of. It's a transformer arrangement. That's the important thing, is the transformer. Just like Myers had the transformer. Transformer. They're all transformers, right? A motor with two windings is going to be a transformer. A motor with, let me restate that, a motor with two windings out of phase, you know, is going to be a transformer. Well, even if they are in phase, but you know, it's a transformer if you really think about it, right? These things can be tamed. Just one other mention here. Mr. Hendershot, Lester Hendershot, had a device that apparently was over Unity, and I've never tried to replicate this. I've looked into a little bit in the past, and I know a little bit about it, right? But I think I understand its operation a lot better now in studying those other things. In just looking at this picture right here, I'm seeing a lot of copper. I think from studying it in the past, I've come to understand that this also is a capacitor. Again, I don't know all the ins and outs, and I haven't researched him, not nearly like I have the others. But I just wanted to mention, you know, here we go, right? Here we go. Same idea, I imagine, right? And the capacitors are interesting, and the fact that he has obviously the same value on both sides next to each inductor. So there we go. I think I'm not going to do another segment. I think I'm just going to wrap it up right here. Let me find a little picture for us to look at. So where's my project headed? You know, hopefully it's obvious, self-explanatory a little bit. I'm going to make an over Unity device, right? Now, I have almost a complete understanding. Now you do too, if you choose to. I need wire to do it, the right type, shape, length, right? As we've seen. The stuff I've used, I really wish that I could have made the resources I do have available to me do what I want it to do now that I understand, but it's not enough. Need a little different wire. Different core material would be nice as well. Those E-cores are a bit of a handicap. I just sort of used them the best way I figured out how to make a demo and to investigate the whole nature of this topic. Anyways, this is where I'm at. That's what I'm doing. So I'll be ordering wire, continuing. I'm going to be making more videos. You're not going to have to wait for them. If you got pissed off about having to wait for my videos, I sort of understand, I guess, but, you know, whatever. Hopefully everyone recognizes that this is this is it, right? This is it. This is hopefully I've connected all the ideas together enough that you see, right, that this is the big idea. And I want to share it with you guys. I just want to say thank you to those who donated things to me in the past. I couldn't have learned the things I have to this point without it. Really, really, really appreciate that. Because, you know, a poor guy like me is hesitant to drop money on things you're unsure of, right? Well, you guys enabled me to get to a point where I'm very, 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 very sure of what I'm doing now. Thank you. Thank you to the person again who sent me the LCR meter. Thank you, thank you. That's the most important tool in the bag. And the tachometer. Someone donated that to me in the past too. Big thanks. And thank you to all my friends who support my spirit amidst an angry, confused YouTube world, right? And me learning how to deal with it. Anyways, haha. So I'm back from a hiatus, you know why, now, and I'll have more vids as normal of good things, right? Hopefully I'll be explaining some of the things I touched on here in more depth and talking about newer things too. Anyway, there you go. Finite. It's a long one, but it had to be. I'll talk to you later. Thank you very much for watching and listening. Hopefully everyone listens. Hopefully some people out there with a little bit of know-how and resources is able to implement this and make an over Unity device. Obviously, you know, me uploading this video really is proof in itself that I don't care about being first or money or anything like that, right? Never, well, I mean, when I was younger, I guess I was motivated by those things, but not anymore. Anyone who knows me knows that, so. Sharing, passing, handing the ball off, kinda, but I'm still going to be working at things and making videos. Again, thank you for watching. Take care, everyone out there. I'll talk to you later.